Hi, everybody. Today we're going to talk about the Galois groups of extensions of number fields and p-adic numbers, and more generally, extensions of the fraction fields of Dedekind domains. And so this sort of splits into two parts. So part one is going to be the local theory. So this is extensions of things like QP. And part two will be sort of the global theory. So this is local theories like QP, FP double parentheses T, C double parentheses T. And the global theory treats extensions of fields like Q, other number fields, FP just single parentheses T. So these are Laurent series, and here these are just rational functions, and so on. Okay, so we want to look at, and we're going to talk about Galois theory and Galois groups. So we're looking at sort of extensions of these fields, and we want to talk about the Galois groups. And well, basically, we want to understand sort of how that interacts with all the theory we've been developing about like absolute values and like factorization of primes and so on. Okay, so that's the goal, and we're not going to do too many proofs today. I just want to sort of lay out the facts for you, and then none of the proofs are actually too hard with all of the theory we've set so far, and you can either work them out yourself or just look in. You can look in Milne, for example, to look up the proofs. Now, by the way, and this is the last subject we're going to do from Milne, and so, well, okay, good. So we'll do some other stuff starting next week. Great. So let's start with the local theory. Okay, and so let me take this set up. So K is going to be a field complete with respect an absolute value, a discrete absolute value. So that just means sort of there are only sort of a discrete set of possible absolute values. And another way to say it is if we look at the ring of integers, which is just the elements in K with absolute value less than or equal to 1. I should give the elements a different name. So it's the elements in K that have absolute value less than or equal to 1. Then this is a complete DVR. It's a discrete valuation ring, so it's a Dedekind domain with a single non-zero prime ideal, and so it's complete for the corresponding absolute value. Okay, so like an examples like this would like OK would be like ZP if K was QP, or like FP double brackets T if you had this one. So power series if you have Laurent series. I'm gonna write if P is the maximal ideal. So, or actually, let me write it this way. Let me write it sort of M sub K. So it's just all of the elements with absolute value less than 1. So strictly less than 1. And then I'll write sort of kappa for the residue field, which is just the field OK mod MK. Okay. So I want to talk about the structure of Galois groups of extensions of K. I'm going to put a hypothesis in that will just hold always for us. I'm going to assume kappa is perfect. So I'm going to assume this residue field is perfect. So for example, it could be FP or it could be C, it could be, so in all of these examples I wrote down above, it's perfect. I don't want to, let me not say anything more, but in some of, if you only think about the examples we've talked about so far, like this is not really a new assumption. This has always been in our examples, and just you can set things up without it, but it will make it slightly easier to just assume this is always holding. Okay, and so I want to sort of study the structure of extensions of L and the structure of Galois groups of Galois extensions, sorry, of extensions of K, and the structure of Galois groups of extensions of K, and sort of how it interacts with sort of like the residue field and the ring of integers and so on. And so before I do that, I just want to make one remark. So that's sort of not really about Galois extensions, just about general extensions. So let me just say as a lemma or theorem. So if I fix an extension L over K, and let's say a finite extension, L over K, and then I write, well, okay, so if I fix a finite extension L over K, then by the theory we already know there's sort of a unique extension of the absolute value to L. And sort of this extension is still going to be discretely valued. So like the ring of integers in L is still going to be complete DVR. So let me sort of write sort of, so here, maybe I should call this kappa sub K. So we're going to write so kappa sub L. That's the ring of integers in L modulo the maximal ideal in L. So this is just saying all things of absolute value less than equal to 1. This is all things of absolute value less than 1, so for the unique extension of the absolute value to L. And when we saw it sort of on the worksheet, the alternative you can think of OL as being the integral closure of OK in L. So that sort of fits into the world of studying extensions of Dedekind domains that we talked about earlier in factorization. Okay, and then the statement is the following. Then there's sort of a natural bijection between subextensions of L and subextensions that are unramified. Sorry. So I look at sort of all the subextensions M that are unramified, and just these subextensions, unramified, I should be precise. I mean, the extension M over K is unramified, not the extension L over M. So these are in bijection with just extensions of the residue field. So let me write okay, so if I look at the subextensions of L that are unramified over K, then those are, and if I have such an extension, then sort of the residue field of M is automatically an extension of the residue field of K that sort of lives between these two. And I'm saying sort of any unramified extension is sort of uniquely characterized by that. And moreover, if I sort of take some intermediate extension of the residue fields, then sort of always comes from a unique such thing. Okay, so somehow the theory of unramified extensions in this case is the exact same as sort of the theory of extensions of the residue field. So for example, if K was QP, then I'd be saying just like the unramified extensions sort of just correspond to correspond to extensions of FP. So this isn't really about Galois theory yet, but this is just sort of a first structural thing. Let me just highlight sort of in particular. There is a largest or a maximal unramified extension. So the maximal unramified subextension, K, let me write this L, so UR, where L sort of and this just corresponds under this bijection to the extension KL, K kappa. Okay, so the point of this theorem is there's some part of the theory, of the extensions of this field K that's sort of just completely described by the extensions of the residue field. So that's the theory of unramified extensions. And well, in particular, this is nice. So I think we said a little bit about this before, but in this case, I mean, we have sort of L over L unramified is sort of totally ramified. And then sort of L unramified over K is unramified. So yeah, we used this statement before, like for example, when we were proving there were only finitely many extensions of QP of a fixed degree, we use this, we could always break down an extension into sort of an unramified part and a totally ramified part. Okay, and so basically what we're going to do for Galois theory is we're going to sort of see, well, if you have a Galois extension, sort of the Galois group of this unramified part is going to be just the Galois group of the finite fields extension, or sorry, of the residue field extension. So it'll just be the Galois group of kappa L over kappa K. And then we'll sort of also sort of refine a little bit, then we'll sort of have the Galois group of this thing. And we'll sort of refine a little bit what that looks like. So we'll sort of filter this a little bit more and sort of break apart how the ramification occurs in this extension, sort of break it up into chunks that you can study one at a time. So that's the idea. Okay, so let me just say the main definition. Oh, and by the way, to prove that theorem, I mean, this is basically just, and the proof is Hensel's lemma. I mean, the proof of this theorem is basically Hensel's lemma. And you have to sort of be a little bit careful, but it's not much more to it. It's just a consequence of Hensel's lemma. Okay, so definition, so if same setting as above, if L over K is Galois, so if L over K is a Galois extension, let me write G is equal to Galois group of L over K. Then I'm going to define sort of subgroups GI. They're actually going to be normal subgroups of G. And they're defined by the identity. So they're all the elements in G such that sigma of alpha, the distance between sigma of alpha and alpha, so it's going to be less than let me write it down and then I'll define all the things. So it would be less than sort of the absolute value of a uniformizer of L to the I. This is sort of for all alpha in OL. So here, pi L generates the maximal ideal in OL. So yeah, okay, let me just say it that way. So recall in the maximal ideal is all things with absolute value less than 1. So this is right. So somehow absolute value of pi L is the absolute value of pi K to the 1 over E, where E is the ramification index. So where pi K generates the maximal ideal in OK. It's one way to think about it, and that sort of part is not so important. I just wanted to sort of recall what this means. Okay, so and what am I defining? Well, I know that there's a unique, and the big thing we sort of saw about these extensions, there's a unique extension of the absolute value on K to an absolute value on L. And so by this uniqueness, we know this absolute value is preserved by the Galois. And so now I'm sort of refining this further. I'm asking, well, I know the Galois group preserves the absolute value, but like, let me also look at sort of how close like things end up when I move them around using the Galois group. So if I sort of take this element alpha and I hit it with some element of the Galois group, like there being this distance being less than sort of the absolute value of pi L to I, and that's saying like if I is big, this is saying that sort of this element doesn't move things very far. So sort of some of the action of the Galois, this Galois element doesn't move things very far. Okay, and I'm sort of just, I'm going to filter the Galois group by this, by these subgroups. And well, as if they're normal, it's sort of an exercise to check, but, and again, it's just going to be because, I mean, it's going to be, I mean, yeah, so, and the reason they're normal is just, because like if you work it out, again, it just follows from the fact that this absolute value is unique, and so sort of it's not sort of moved around when I hit it with some element of the Galois group. Okay, but you can just work out the formula yourself. So let me state the main result then about these. So first thing is sort of, and this is a chain of normal subgroups, and it really exhausts everything. So the identity element is equal to the intersection of all these subgroups. So I mean, some of the only thing that's sort of in these GI for I big enough is the identity element. When again, this is basically rudimentary to check. You're saying, and if you're saying it's in all these subgroups, if like some automorphism in all these subgroups, that means sort of like no matter how close you look, sort of it moves everything that close to each other, that close to itself. And so, and somehow if sigma of alpha minus alpha is less than sort of arbitrarily small things, then sort of sigma alpha has to be equal to alpha. This absolute value is just 0. So that's all this is saying. But good. So this is, I mean, somehow this is a filtration. And this is an exhaustive filtration of the Galois group. The second thing is, if I look at G mod G naught, well, this is actually just going to be the Galois group of the residue field extension. So what I mean equals that? Well, what is G naught? It's everything that's, and so G naught is sort of, let me sort of write this in. Another way to write the definition of G naught is just sigma, such that sigma of alpha is congruent to alpha mod the maximal ideal in L. If you sort of think about this means, so here I is 0, so you're just saying sort of sigma of alpha minus alpha is less than 1. But saying it's less than 1 just means it's in the maximal ideal. Okay, so that means sort of this is all the thing. The way to say it is, oops. And so this G naught is literally there is, yeah. So that because the maximal ideal is preserved, like there's always a map from G to here, from the Galois group of L over K to the Galois group of KL over KK, or kappa L over kappa K, so from the Galois group of the field extension to the Galois group of the residue field. And then sort of this is just like if you plug in I equals 0 here, you just have a different way of writing down what it means to be in the kernel of that map. And then the only thing to check is that this map is surjective, but that sort of follows from this map from G mod G naught to this Galois group. That follows essentially from this previous theorem that unramified extensions match up with extensions of the residue field. Okay, so that's what's going there. And then, okay, the next thing is about G naught mod G1. So G naught mod G1 is going to inject into sorry, G naught mod G1 injects into kappa L cross. And then for I greater than 1, for I greater than or equal to 1, GI mod GI plus 1 injects just into kappa L. Okay, so here, and this just means the non-zero elements in the residue field viewed as a group, in particular this is an abelian group. Here, this means all of the elements of kappa L sort of viewed as a group. And here, basically the point is, so this is for I greater than or equal to 1. This is number 4. And the main point in seeing these is you can actually check in this definition. Well, the way I wrote down this definition here, I had to check sort of for every alpha that this distance was less than pi L to the I. But for I equals 1, for I greater than or equal to 1, sort of GI is equal to sort of just actually a set of sigma and G such that they move a uniformizer. By that much. So somehow, once you've sort of gone down a few steps to G1, instead of checking every element, it turns out to suffice to just check on this sort of single element on the uniformizer. Okay, and so then this map is sort of, this first map is, this goes to sigma maps to sigma of pi L over pi L, and sort of some mod ML. So that's sort of what this map is. You sort of just look at the ratio between these two, you reduce it mod maximal ideal, and well, you can check that's well defined and really gives you sort of this objective homomorphism. And then I'll let you write it down here, but you do something similar for this one. Okay, good. So that's pretty interesting because this sort of has the following corollary. If the Galois group of the residue field extension is solvable, then so is the Galois group of the whole thing. So, for example, so if K is equal to QP, then so the Galois group of any extension is solvable. This is because so the residue field of QP is just FP. Sort of every extension of FP is not only solvable, every extension of FP is abelian. I mean, every extension of FP is sort of has cyclic Galois group because it's given by FQ, and then sort of the Galois group is generated by the Frobenius substitution, x goes to x to the p. Okay, and so that part is sort of this quotient is abelian, but in all these other quotients are always abelian. So that's sort of what this is saying. I mean, because KL cross, like that's just the units in the field, that's an abelian group. Kappa L cross, and then kappa L, again, this is the residue field, this is under addition. So this is just an abelian group. So the only thing sort of that would ever stop this from being a solvable group would be if the residue field extension was not solvable. Okay, so and that's pretty, yeah, and this is a pretty strong statement that this Galois group is solvable, and this is sort of quite nice. I mean, again, this is sort of some way in which, I mean, this explains in some sense why sort of like looking at QP is sort of simpler than looking at Q, and like why it can help you look at why it can help you sort of in solving problems to work over QP instead of Q. So you can sort of understand some part of what's going on, but there are like structural aspects that are simpler. So in particular, Galois groups are solvable. Okay, great. and this is the main structure theory. So these GI are called, probably I should run that. So these GI are called sort of ramification groups. And when one of your exercises, you'll compute this in sort of a simple example, just to sort of get a little bit better idea of what's going on here. Let me connect this to one other thing that's also related to some of the other worksheets, and then we'll move on to sort of the not local theory. So let me just recall sort of a definition. I think I'm recalling it, but actually I might have never defined it before. So L over K is, well, it's unramified if E is equal to 1. So this is any extension. So E is the ramification degree, and sort of the ramification degree is 1, then it's unramified. Okay, that's nothing new. L over K is tamely ramified if the characteristic of the residue field does not divide the ramification degree. And so it's wildly ramified otherwise. So for example, and if the residue field has characteristic 0, like if your field is like Laurent series over the complex numbers, then everything is, like every extension is tamely ramified. But sort of if the residue field has characteristic P, so like QP, then sort of an extension that's ramified, that has ramification degree P, like is wildly ramified, not tamely ramified. So there's sort of, there are a couple exercises about this notion on your homework. I mean, tamely ramified really means somehow things behave much better. And yeah, so some things on the worksheet make that precise. But let me just sort of state the main connection here. So another corollary of this theorem above is that if L over K is Galois, then, well, L over K is unramified if and only if G naught is the identity element. And L over K is tamely ramified only if G1 is a trivial subgroup. So in particular, sort of L, the fixed field of G naught inside of L is just the maximal unramified subextension I was talking about earlier. Okay. Maybe I'll say LG1 is the maximal tamely ramified subextension. So it's maybe and essentially it follows from your exercises, but you can think about why it makes sense to say maximal tamely ramified subextension. Okay, well, so that's the local theory. So just to recap, if you have a field that's complete with respect to a discrete absolute value, so like QP or a Laurent series field, then well, first sort of unramified extensions just correspond to extensions of the residue field. And then you have a nice filtration on the Galois group. You sort of just basically filter by looking at sort of elements that sort of map everything, elements of the Galois group, so automorphisms of the field that sort of map everything to something else that's very close by. And so that gives you this filtration by these ramification groups GI. And then it turns out sort of, and this is useful because So this filtration by normal subgroups that exhausts the whole group, and the quotients are very understandable. So the first quotient, G mod G naught, is just a Galois group of the residue field extension. Like in particular, if the residue field is a finite field, like in sort of if it's QP or like sort of the completion of a number field, that's always going to be the case. Then this part is very simple, and then the rest sort of just injects into all the other steps. The quotients just inject in sort of these abelian groups, just given by the residue field. And so in particular, sort of the Galois group is solvable, and sort of, but more than being solvable, you have some nice explicit presentation of it being solvable. Okay, and so those are sort of the main points of this local theory. Okay, so now I want to sort of talk about the global setup. Okay, so here we can just take K to be the fraction field of OK, where sort of OK just is sort of any is a Dedekind domain. And let me just assume I want to match up part of this with sort of local theory. So let me just assume sort of the same condition that OK mod P is perfect for any non-zero prime. So prime ideal P. So e.g. K could be Q, in which case OK would, well, I could take the ring of integers. And I could sort of take other OKs inside of here to start with, or I could take the integers, or I could take sort of integers that convert some primes. But okay, let me just take the integers. That's sort of the standard example. I could have K FQ parentheses T, and OK could be FQ brackets T. I could have K to be C parentheses T, so functions one variable, rational functions one variable, and OK, C brackets T. So this example works with any perfect field as the coefficients. Okay, and so maybe the most important to keep in mind though is this one, and sort of more generally, K could be a number field, and OK just a ring of integers, which is just the integral closure, would be the integral closure of Z inside of K. Okay, so I'm going to look at a Galois extension now. So suppose L over K is Galois. And I want to sort of use the structure of like prime ideals and factorization to sort of define some natural subgroups that let me sort of understand and sort of relate to the structure of factorization and relate to the structure of the Galois group, relate to the structure of like extensions of local fields. Okay, so let me say it this way. So if Q is a prime ideal, so OL, as usual, is just the integral closure of OK. Now, and so if Q inside of OL is a prime ideal, I can define the following. I'll split up the definition. So the decomposition group D of Q. Again, I'll write G is the Galois group of L over K. So this decomposition group D of Q is just the stabilizer of this ideal. This is all of the sigma of the sigma in the Galois group such that sigma of Q equals Q. And so the word here is an order. So okay, so this is going to be a subgroup G. Not necessarily a normal subgroup, but this will be a subgroup G. Well, any element of the Galois group sort of preserves the ring of integers, and then so in Galois group sort of starts as just an automorphism L that fixes K. But I mean, somehow it's going to sort of, if you think about the definition of the integral closure, like it's also going to fix, that means it's also going to fix OL. So it's going to map OL to it. Sorry, it's going to map, since it fixes K, it's going to map sort of elements that are integral over K, OK to elements that are integral over OK. So sort of the Galois group acts on OL, and then it sort of will send prime ideal, like it sends ideals to ideals, and will send prime ideals to other prime ideals. And so, okay, sort of in particular, sort of G acts on the set of prime ideals in OL, and then this is just saying I'm looking at the stabilizer of this prime ideal Q. Okay, and so let me just sort of state a quick lemma. Well, this decomposition group at Q is going to be equal to, or sorry, isomorphic to the Galois group of the completion of L at Q over the completion of K at P, where P is just sort of the prime that Q lies over. Okay, so how do I see this? Well, I mean, saying you preserve like saying this element of the Galois group sort of preserves the ideal Q, that's actually, it's basically the same as saying it preserves the Q-adic absolute value. So sort of this element Q sort of defines some absolute value L on K, which is sort of then L sub Q is just completion for that. And if you think about this, like preserving the Galois group preserves this prime ideal, then it preserves that absolute value. And so sort of all the automorphisms sort of are continuous for this topology, and so they extend sort of automorphisms of the completion. And I mean, somehow, because they preserve K and because they preserve Q, they also preserve this ideal on the intersection. And so sort of these automorphisms fix this field here. On the other hand, sort of, on the other hand, yeah, okay, well, let me say that, and then you still have to say something to see that so you get a natural map, this decomposition group over here, and this map will be an injection. I mean, somehow, okay, so the exercise, and then you can also show us a surjection. So there's some work to do here, but you end up finding this decomposition group is isomorphic to the Galois group of sort of this extension of now complete fields. Okay, and so let me sort of draw now sort of the whole picture. So we have yeah, okay, so let me make some follow-up definitions then. Sort of IQ, the inertia group, just the pre-image of G sub 0. So, okay, so over here, I have the ramification filtration. Let me write it this way. So on this sort of extension of local fields, I'm sorry, not local, but on this extension of sort of these complete fields, I have the ramification filtration. Let me just define the inertia group to sort of be the pre-image of the Galois group under this isomorphism. So this is sort of a subgroup of the decomposition group. Good, and I think that's sort of all I want to sort of draw in this picture. And so here's so here's the picture that sort of describes how everything works. Sort of the most important picture to keep in mind when you're sort of thinking about Galois theory of extensions of this sort, like extensions of number fields in particular. So we have L sort of sitting up here, and then we're looking at sort of the specific prime ideal Q. And sort of way down at the bottom down here of this diagram, we're going to have our field K. And here we have a prime ideal P. So, I mean, just sort of from factorization, we know sort of Q is, so from factorization in Dedekind domains, we know Q is going to be sort of P to the E, P is sort of equal to P1, P2 to the E, P G to the E. So G is sort of the number of primes that divide Q. And then E is the ramification degree. And because we're in a Galois extension, the ramification degree is the same for every prime. And then and then sort of so we have sort of L colon K equal to E F G. So E is the ramification degree, F is sort of the degree of the residue field extension. So this is the degree of OK mod Q, so OL mod Q over OK mod P. Sorry, I wrote everything backwards. Let me try this again. This was supposed to be so the prime ideal P is in the bottom. That factors as sort of Q to the E. So I sort of fixed out this one, and then I have sort of these other prime ideals Q, G to E. Okay, good. So that's the setup. Then and I have these subgroups now, this decomposition group, and I have the inertia subgroup. So I can sort of look at the fixed fields. So here I have the fixed field for the inertia subgroup. Here I have the fixed field for the decomposition group. Then that lies over K. And well, the E, F, and G give me the degrees of this extension. So this last part sees all of the ramification. This middle part just sees the residue field extension. And then this first part sees the number of prime ideals that splits in. So the reason you get a G here, like the number of prime ideals that P splits in, is just because you can show that the Galois group sort of acts transitively on this sort of set of prime ideals. I can't remember if we did talk about this before or not. This is a good exercise if we didn't talk about it. But so the Galois group acts transitively on this set of prime ideals. And now sort of just this decomposition group is defined to be the stabilizer of one element. So sort of the orbit stabilizer theorem tells you that you get this G here for the degree of this extension. Right, and then okay, so this is the residue field extension, this is the inertia extension. And this part just sort of comes from the local theory, because here sort of this maps into, oops, let me say it this way. So K maps into the completion of K at P. And well, if you think about it, you see that this extends to an injection from the sort of fixed field for the decomposition group into KP. So it's sort of another exercise to see why this injection is here. But now, sort of at the top of here, we have sort of the completion of L at this prime ideal Q. Of course, that injects here. And then here we just have sort of the fixed field for the inertia group, which is sort of just G naught. Okay, and we have sort of this tower of extensions. And then sort of over here, this is sort of not, okay, so and this is still F and E. So this is just like before. And so this part is sort of, in this extension is unramified. Oops. This extension is ramified. Okay, and then sort of this unramified extension sort of corresponds via this bijection between extension of the residue field. This is sort of right, sort of kappa sub Q. So this means sort of the residue field of this guy, or sort of it's just OL mod Q. This is an extension of kappa of P. It's the residue field of this guy, so it's just OK mod P. This is sort of this F. Okay, so yeah, okay. So and this is sort of somehow an extremely useful diagram. Sort of encodes everything. It encodes everything about the relation between sort of factorization, like sort of this prime sort of that lies above P, and sort of how that relates to Galois theory. And sort of let me sort of, okay, so this is sort of a big theorem, is that you have this diagram. I'll sort of move this Q and P over closer. And let me just say sort of, so let me, yeah, since I'm saying it's a theorem, let me sort of highlight one point here, which is this G here. That's just the fact that sort of this extension is degree G. This is the same, literally the same by the orbit stabilizer is saying that gal L over K acts transitively on the sort of primes dividing P. Okay, good. So this sort of encodes sort of everything about the relation between factorization and sort of these Galois groups and everything. And so maybe sort of another consequence of that is sort of if Q1 and Q2 sort of divide the same prime P, then dQ1 and sort of dQ2 or IQ1, the inertia subgroups and decomposition groups for these two primes are conjugate. Of course, sort of also another thing you see here is sort of in the Galois extension, like the completions are also isomorphic to LQ2. Like the completion, so in the Galois extension, the completions sort of for two primes lying above it are isomorphic, and so the residue fields are also isomorphic. So this isn't true sort of in a non-Galois extension, but sort of in the Galois extension, the fact that sort of the Galois group acts transitively on the primes dividing P, well, sort of that means it sort of also acts transitively on sort of the different absolute values. And that sort of gives you, sort of that induces sort of an isomorphism on the completions. So sort of, if you take an element of the Galois group that sort of maps Q1 to Q2, then sort of that induces an isomorphism from the completion with respect to the absolute value defined by Q1 to the completion with respect to absolute value defined by Q2. Okay, so and this is somehow some super powerful structure that you can really use to sort of both, you can use it to understand Galois groups, and you can use it to understand prime factorization and sort of how they mix in powerful and interesting ways. So let me sort of highlight one aspect of this that turns out to be very, very important. One important consequence of this diagram. Let me sort of just say in the simplest case. So if L is an extension of Q, then need to sort of, if P is unramified, in L, so P is just a prime number now. So P is equal to Q1 times QG. And then sort of for each of these elements, I sort of have sort of decomposition group DQI is contained in the Galois group of L over Q. Good, but this is also sort of just isomorphic to the Galois group of OL mod QI over, so this is just the residue field over this is over sort of just FP. And well, this is just sort of extension of finite fields. So this is just sort of that Galois group of sort of F sub P to the F over FP. And sort of, okay, this doesn't really make sense, but it just means sort of any finite field of order P to the F. And this is just generated by the Frobenius element. So the map X goes to X to P is an automorphism of any finite field. It's sort of the automorphism fixes FP, and this generates the Galois group. So you have sort of a distinguished element. You sort of have a distinguished element in here, which gives you a distinguished element in here, which gives you sort of a distinguished element in here, which gives you a distinguished element in your Galois group. So sort of so QI gives you an element. People sort of write this different ways. Let me write it as L I L Q I contain. So okay, this is just notation. So this is just a way to say it's an element attached to this extension L over Q, sort of, and the prime ideal QI. And this is contained in the Galois group of L over Q. This is called the Frobenius IQI. Okay. When there's sort of, so this is sort of some distinguished element, and well, I'm going to sort of change my perspective a little bit. I just want to sort of think about sort of something attached just to this prime number P instead of all of the instead of sort of having to pick a prime above it. And well, the point is sort of so these are conjugates. In fact, these form a constancy class. And gal L over Q. as sort of I varies. So if I look at sort of all of the different factors of P, all the prime ideals appearing in the factorization of P in OL, then I get a sort of a conjugacy class, and I sort of take this distinguished Frobenius element, trace back these isomorphisms, I end up with just sort of, so I end up with a conjugacy class of elements in Galois over Q. So this is sort of the Frobenius conjugacy class. Attached to P. Okay. Okay, and so it turns out sort of studying these Frobenius elements or Frobenius conjugacy classes is sort of extremely powerful. So just sort of an example. And so you basically, we didn't write quite this way, but if you look back at this exercise where you proved quadratic reciprocity, like the way you did it was using these elements. You do this using sort of the Frobenius Galois elements in sort of Q zeta P over Q. Okay. And so sort of this idea, sort of this generalizes, so if you sort of think about what happens here, you sort of think very, very hard and you're someone famous, then you'll sort of invent class field theory, or alternatively, you could just read a book about class field theory. But I mean, somehow this idea is sort of very, very important. And I mean, all of the, like, a lot of modern number theory, for example, the area I work in, sort of studies sort of representations of Galois groups and their relation to sort of other objects, and the relation between representation of Galois groups to other sort of objects that are interesting in arithmetic sort of all come from this fact that, like, inside of any Galois group, sort of you have sort of natural elements or conjugacy classes attached to prime numbers. And so this is sort of a very, very, very important idea in modern way of thinking about number theory. Okay, yes, so may I just want to highlight that. I'll just say out loud sort of another result. So it turns out sort of these Frobenius elements sort of generate the Galois group. So like sort of very overall unramified primes, I guess sort of things that generate the Galois group of any extension. And like even stronger than that, they actually sort of as P gets bigger, they sort of equidistribute in the conjugacy classes. So sort of the Frobenius conjugacy classes, if the number of primes sort of less than some big number that are in a given conjugacy, like whose Frobenius is a given conjugacy class, will be sort of proportionate to the size of that conjugacy class. So that's the Chebotarev density theorem. And this is sort of a very, again, sort of a very powerful theorem. One application of this that you'll see a little bit about if you look in Milne or in sort of one of the exercises sort of asks you to do this on the worksheet is that you can use sort of this equidistribution statement and sort of some effective version of it that says how far you have to go to sort of see every conjugacy class to give sort of an effective algorithm for computing Galois groups of polynomials. I mean, it really tells you can actually reduce computing the Galois groups of polynomials to just factoring polynomials mod P for sort of sufficiently large P. So somehow it's a fairly powerful algorithm. Okay, so right, I think this is probably a good place to stop for now. So I'll see you in class on Tuesday.